Okay, so in this lecture, we're going to be talking about Chapter 9, which is SN1 and SN2 reactions and also E1 and E2 reactions. We're going to start this lecture and only talk about SN1 and SN2 reactions. Also, I wanted to tell you, I did finish the lab problem set for SN2 lab, the virtual lab that you're going to do. I didn't put it in where the other problem sets are. I actually attached it to the assignment so you can get the problem set right from the assignment. It's an attachment, not copy and paste it into the body of the directions like last time. Okay. When we're talking about SN1 and SN2 reactions, what we are talking about is nucleophilic substitution, getting a nucleophile onto a carbon chain. Okay. Now there's two things we're going to talk about here. We're going to talk about the nucleophile, and that is our Lewis base, if you remember. Those are the ones that are donating the electrons. And then we're also going to be talking about the leaving group. That's the group that literally gets kicked off in this process. So in the end, the nucleophile will take the place of the leaving group and will be left with a leaving group as part of the product. So when we talk about, again, the nucleophile, we're talking about nucleus loving. It has the electrons to donate, and the leaving group is just displaced in a substitution, or it's lost by an elimination. So the S in SN1 and 2 is substitution. The E in E1 and E2 is elimination. Our electrophile is the thing that is electron loving. It is our Lewis acid. It is accepting the electrons from the nucleophile. So with our electrons that are being donated, we are going to get what we call an electrostatic potential map that shows the nucleophile reacting at its negative end, and the electrophile in the reaction, kind of like the partially positive end. Okay. So if we look here at just an example, we have our nucleophile, which is the hydroxyl group. It's got a lot of electrons with that oxygen, and it's going to come in and attack the carbon, which is the electrophile, and kick off the chlorine. And in the end, what we get is a chlorine atom all by itself, and that hydroxyl group is now attached to the carbon group. So when we're talking about here, these are just common electrophiles and nucleophiles. Oh no, this is just the nucleophile. Just kidding. So we have common nucleophiles, and we're going to talk about how those nucleophiles are rated as better or worse. But this is just a summary of what you get depending upon what your nucleophile is going to be and going to add on to the carbon group. Become familiar with these. Here, you need to become familiar with these based on what the incoming group is and what, your final product is going to be. I highly recommend making flashcards for this. Okay, so the two mechanisms with substitution are SN2 and SN1. The only difference between them is the way in which the bonds break and form. Okay, so in an SN2 reaction mechanism, the bonds breaking and the bonds forming are happening at the same time. So when the departure group, when the leaving group is departuring, when it's going away and getting kicked off or substituted out, that is happening at the same time that the nucleophile is coming in. So for example, here in an SN2 reaction, first of all, we see this when there are very small surrounding groups. So for example, hydrogens, those are very small groups comparatively that are surrounding carbon. When we have those real small groups surrounding the electrophile, which is the carbon, it's very easy for this hydroxide to come in and attack it while simultaneously the bromine group is coming off. This is the SN2 reactions have an intermediate, and you see it right here, where as these bonds, that bond is forming, this bond is breaking. And in the end, what we're going to get is the hydroxyl group we're going to get the hydroxyl group that will go ahead and attach, and we will get the bromine group, which will be off and substituted out. You'll note in the reactant side the stereochemistry of these hydrogens and how they switch when the hydroxyl group comes in. Here's an energy diagram. You can see that the transition state is a much higher energy, but in the end, the net is that the product has much less energy than the reactants or the intermediate transition state. So this transition state wants to go pretty quickly because it's very high in energy and it doesn't like that. So when we talk about these bond breakings, we're talking about the bond between the carbon and the leaving group. And in the SN1 reaction, the difference is that bond breaking between the carbon and the leaving group must happen first in an SN1 reaction. Only after that bond is completely broken will the nucleophile come in and attach. So for example, here our leaving group is a bromine. Note, by the way, the attachments to the electrophile are these really big methyl groups. Because of their size, it's really hard for a nucleophile to come in and attack that electrophile simultaneously. So once the bromine is gone, that's when the carbon can become more open to attack. All right, so there can't be a back attack like in SN2. First, the leaving group has to go, so there can be this rearrangement of stereochemistry. Then a nucleophile can come in and attack because it has room. It can't get in here because it's too bulky. There's nowhere for that nucleophile to come in. So the leaving group here is the rate determining step. It's the slow step. Recall from Gen Chem 1 and 2, the slow step is always the rate determining step. Once that happens, now the nucleophile, in this case a methanol, can come in and it will attack that carbocation intermediate. You'll note in SN2 reactions, there was no radical or carbocation intermediate, but in SN1, because the leaving group leaves first, that carbocation intermediate forms. You can see it right here. And then this nucleophile, in this case methanol, can come in and attack, leaving us with this final product. Okay? Now, once we have that methanol attached, another methanol is going to come in and remove that hydrogen. So in the end, what we get is a tert-butyl methyl ether. So here's our tert-butyl, remember our chicken foot. With this, okay? And then, of course, we get this product as well. Now, here we have several transition states. The first transition state is the formation of that carbocation. The second transition state is the energy of activation needed for that, in this case, methanol group to come in and attach as the nucleophile, come and attacks the carbocation. And the third transition state is the removal of that hydrogen from the methanol. So what are the things that you should consider here? I'm not going to go through each and every one of these. That's what the next several slides are. I'm going to talk about a few of them, but most of them are just definitions and what really does affect what. All right, so questions you need to be thinking about. What are the kinetics and stereochemistry of SN2 and SN1 mechanisms? What effect do the following structures have on the rate of reaction? What is the role of the solvent? Under what conditions are skeletal rearrangements observed? I'm not going to go through each and every single one of these. Most of these are definitions, like I said. But you need to go through and make sure that you understand what's happening, okay? Keep in mind, I am going to... This is the chapter where I'm going to post supplementary YouTube videos from one particular YouTube guy. You've heard me talk about him, the organic tutor. He goes through tons of SN2 and SN1 reactions for examples. And at the end of, I can't remember which one it is, but one of them at the end, he gives you a reaction summary of how you can quickly pinpoint whether it's going to be SN1, SN2, and whether or not stereochemistry matters. He also does one that includes E1 and E2. So I would go ahead and make that chart also, copy it from him, and start learning it, okay? All right, so the most important thing you need to understand about the kinetics is that SN1 mechanisms are first order reaction. It occurs in 2 steps. And the slow step is the rate determining step, and that slow step is the leaving group coming off. SN2 reaction mechanisms are second order because the haloalkane and the nucleophile, both of those, both the back attack and the leaving group leaving, those are both for first order reactions. Sorry guys, words are hard today. Those are both first order reactions, and therefore overall it's a second order reaction mechanism. Okay, so any substitution, this right here is super important. Any substitution whose rate depends on both the leaving group and the nucleophile is an SN2 reaction. If the rate is determined only by the leaving group, then it's a SN1 reaction mechanism. So big takeaway from stereochemistry is that we have chiral centers, and so when either an enantiomer of the molecule goes under SN1 reactions, you're going to get a racemic mixture, and they are going to be enantiomeric products with the S and R enantiomers. What's happening? There we go. Something's wrong with my little pen I'm writing with. Sorry, it's not letting me change pictures or slides. When we talk about SN2 stereochemistry, because of the backside attack by the nucleus, we get the inversion. So if we had a wedged, we would get a dashed. Now I realize this is kind of confusing because they're using both iodines here, but what they're saying is I already have an iodine substituted alkane, and this nucleophile is going to come in a backside attack and kick this iodine off, and what that leaves us with is an inverted iodine, so now a wedged iodine, and this iodine came off, okay? So the rate of the racemic mixture is twice the rate of when we talk about pure octanes versus something else that's happening, okay? So before you saw an octane and you see this huge R group here, this hydrogen that's next to it allows this back attack and that iodine to be kicked off. When we talk about rate determining steps, we're talking about what's happening, whether or not we're going to get a carbocation, and if we do, where that is going to occur. As we know, we've already talked about many, many times this semester, tertiary carbocations are more stable than secondary, which are more stable than primary. So the only time we're really going to get this allelic carbocation, remember the one that's next to the double bond? That's going to be a primary. Whenever we get that primary, the only way we can really it can only really happen is if we get that stabilization from the double bond. So again, we can classify these as primary, secondary, tertiary. Same with the benzylic carbocations. They generally have about the same stability as the allelic carbocations, but they can all be stabilized by the delocalization. All right, I'm just going to mention this very quickly because this is going to have a lot to do with when we get to eliminations. When we talk about alpha and beta branches, we're talking about, is the branch up or is it down? Okay, now this is how I remember it. Beta, it's a bee. It flies high in the sky like a bird. Alpha looks like a fish. Fish swim under the sea. It's down. So a beta branch is up. If this were an alpha branch, we'd see this. Okay, that would be our alpha, down swimming with the fishes. Beta, up flying with the birds. Okay, so how many branches affects the rate? So just kind of keep this in mind. Note how the rate is decreasing with more branches attached. Now, SN1 reactions, this is these two things you really need to understand. SN1 reactions are driven by electronic factors. And what that means is how stable is the carbocation intermediate. If it's a very stable carbocation intermediate, it's going to go pretty smoothly. SN2 reactions are driven by steric factors. So how easily is the electrophile accessible by the nucleophile? Okay, so for that, we're looking at size and what that electrophile is going to be attached to. Is attached to just hydrogens, one methyl group and a few hydrogens, all methyl groups. Okay, so how big and bulky are the things surrounding the electrophile in which the nucleophile will come in that back attack? Okay, so you can understand just on the basics. We know with SN1, if we need a carbocation stability, then we're looking at tertiary to be the most stable. But with a tertiary carbon, that's not really, unless there's only hydrogens surrounding that carbon, that's not really great because, you know, a tertiary carbon, that's going to block that nucleophile for coming in. So if we got a tertiary carbon, that's going to go through SN1. If we got a primary carbon, that's almost always going to go SN2 reactions. Relatively leaving groups, or groups that leave with relative ease, you pretty much see from here down. I would memorize that. You almost never see these as leaving groups. And if you do, it's because something really, really strong has come in. So the more stable the ion is, the more readily it will be a leaving group. And that's why you don't really see these as leaving groups very often, because their anions are not very stable, not compared to, say, for something like iodine or bromine ions. The protic solvents, you need to go through these and understand what each type is. Here's some examples of them. More examples. These you don't have to memorize, but you do need to become familiar with them, because once you start seeing things in reaction mechanisms like DMSO, you got to recognize that as a solvent, or DMF or THF. You know, you got to recognize these as solvents. The non-polar ones I would memorize because it's just easy. There's only 3 of them that are going to be the most common for you. But you just got to be familiar with what we're talking about here. The other thing you need to keep in mind is when we talk about this dielectric constant, the better the solvent, the higher the number. So we look for things that have a number greater than 15. So if I were to compare, for example, this one with, say, this one, the DMSO and acetone, the DMSO is going to be the better solvent because we know that because it's got a higher dielectric constant. The effects on the solvents, the effect of the solvent on the nucleophile and the what's really happening in SN1 reactions, you need to go through these definitions. Now let's talk about this. The most common type of an SN2 reaction is when we will have the negatively charged nucleophile and a negatively charged leaving group. So good examples of that are maybe a bromine ion is going to come in and kick off an iodine ion. Okay. Or maybe chloride is coming in and kicking off a bromide, for example. Okay. So the weaker the solvation means the ability to be a solvent, the ability to dissolve. The weaker the solvation of the nucleophile, the less energy needed to remove it. So what does that mean? That means if that bond of the leaving group is real easy to break, the quicker the SN2 reaction is going to occur because it needs way less energy. So rates are affected 100% by the function of the solvent. All right. We can also, by the way, refer to what we've been referring to as nucleophile and electrophile. Right. This would be our nuke, and this would be our electrophile. Okay. We can also refer to them as solvent and solvent type. Don't get confused about that. All right. So the rate of the solvent versus per the rate of methanol, this is where we're getting our relationship or our ratio to see what's happening. So when we talk about nucleophilicity, what we are talking about is the rate at which the nucleophile goes through this substitution, okay, goes through this SN2 reaction. How quickly does the nucleophile back attack to kick off the leaving group? Now, if you haven't done your lab before watching this, you're going to see that there's, when you do your lab, there's a time in which you let the test tube sit and just to see if a reaction happens or not. And it's going to happen relatively quickly. I mean, it's not like snap your fingers and it happens, but it does happen in a relatively short amount of time. Okay. Now, when we talk about the correlations between the nucleophilicity and the basicity, we're talking about nucleophiles and the Bronsted-Lowry bases. So basicity here, equilibrium property measured by the position of the equilibrium in an acid-base reaction. Keep that in mind always. So the effectiveness of nucleophiles increases on this chart. Again, you don't have to memorize this. You will be able to use this on a test, but you need to know how to use it. It is used very similarly to the activity series. Okay? So, but in this case, it's not what metal's going to come in. It's about what the good nucleophiles are or the good solvents are. So when we talk about halide ions in polar protic solvents, they're very different than in polar aprotic solvents. So when we look at the halides and how good of a nucleophile they are, how good of a solvent they are, in polar aprotic solvents, you notice iodine ion is the worst and fluorine ion is the best. Where in polar protic solvents, it's the reverse. Fluorine is the worst, iodine is the best. Why does this happen? When we talk about polar aprotic solvents, meaning aprotic, A meaning lack of, protic meaning hydrogen ion, it's the basicity that says how good a nucleophile something will be. Okay? Anions are weakly solvated, and therefore they can participate in the SN2 reactions very easily. They're so weak that they just readily go backside attack, kick off the leaving group. In the protic solvents, now we have polarizability. Well, what does that mean? You got hydrogens involved now. There are hydrogen ions involved. So now the anions are highly solvated because of the hydrogen bonding. There's hydrogen bondings involved. So now they're not going to go very quickly. We're kind of thrown back to intermolecular forces here. The weaker the bond, the easier it breaks, the easier it forms. The stronger the bond, the harder it is to break, the less likely to react. Or it will react, but just in less speed, rate, and frequency. I want you to go through each individual ion and see how the negative effect is, the negative charge on the ion is affected by whether or not it's protic or aprotic solvents. So our generic trend is that good leaving groups, good nucleophilicity increases left to right on the periodic table. So in SN1 reaction mechanisms, not only are rearrangements common, but they are necessary. So when I look at 2-chloro-3-phenylbutane here, and I see I got methanol as my nucleophile, what we're going to see is the methanol is actually going to attach, if I count them, 1, 2, 3, 1, 2, 3. It's actually going to attach to carbon 3 instead of what we would think would have been carbon 2, because chlorine there is going to be the leaving group to form a chloride ion. Okay? So what's happening? First, the chlorine gets kicked off to form a chloride ion, and we get a secondary carbocation. However, we will have a 1,2 hydride shift so that we can have this tertiary carbocation intermediate, which is much more stable. Once I get that tertiary carbocation intermediate, now the methanol can come in, attack the carbocation, and attack at carbon 3. The last step is to deprotonate the methanol. So another methanol will come in, attack that hydrogen, and pull it off, leaving your final product of those two things right there. So this is just a generic overview of what's favored for type of reaction, SN2 or SN1. So methyl group with a halogen, it's SN2 favored. It's very easy. All 3 hydrogens are super small. Back attack can readily come in, kicking off the halogen, good to go. Same with a primary and secondary alkyl halide, but a secondary only in aprotic solvents that have really, really, really good nucleophiles. Okay. Tertiary SN2 never occurs. Substitution at chiral center, you get inversion configuration. So what does that mean? If you had a wedge, you're going to go to a dashed. All right, that's it for this lecture on SN1 and SN2 reactions. I'm going to upload this, and then just below it, you will see the YouTube video upload of the worked out problems. I don't have any videos of working those problems out from previous semesters, nor do I have the ability to do that at home. Please remember to shelter in place. Keep washing your hands. Wash common areas 2 to 3 times a day minimum with some sort of bleach, Lysol, solution. They don't have to be wipes. It's actually more cost efficient and more green if you spray your countertops and use a dishcloth and then wash it. Okay. 2 to 3 times a day. Don't forget things like light switches, door handles, remotes, your cell phones, your keyboards, your refrigerator handles, toilet flushers, like the actual thing you press down to flush the toilet. Anything you touch more than once a day. The buttons on your microwave. Okay. Doing that makes all the difference in the world. Stay healthy, stay safe. Don't go out unless you absolutely have to. Please, we're begging you. See you on the flip side.